For section 4.4, we're going to look at the graphs of secant and cosecant functions, and this is our final graphing section. Yay, I know. Okay, so the good news about secant and cosecant is that if you can graph sine and cosine, or I guess I should say cosine and sine, then you can graph secant and cosecant. So technically there's nothing new to learn, but it is an odd concept to kind of wrap your brain around. So here's the deal. To graph any secant or cosecant, you are first going to graph the reciprocal guide function as a dotted graph. Okay? Now note that the period of secant and cosecant is 2 pi over b. The only two that are not 2 pi over b are tangent and cotangent. Here's what you do. Choose a guide function and graph it dotted. So if you have a cosecant graph, like y equals c plus a cosecant of b parentheses x minus d, all you do is pretend that that's actually a sine rather than a cosecant. You keep all of the numbers and variables the same, and you simply switch out the cosecant with its reciprocal sine. That is called the guide function. If you have a secant function, for example, y equals c plus a secant of b parentheses x minus d, you simply graph y equals c plus a cosine b parentheses x minus d, but you graph it dotted. So the reciprocal function's keeping all of the variables and numbers the same, but only switching out the trig function. That's called the guide function. Then you insert vertical asymptotes at points that would be the x-intercepts before you shift vertically. In other words, you insert vertical asymptotes at the points that go through the midline of that wave for sine or cosine. Right? Those will always run through the midline. Then you simply keep the maximum and minimum points from the crests and the troughs from the dotted graph as the vertices of your parabolas. So these guys actually form infinitely many upward and downward parabolas separated by vertical asymptotes.
And keep maximum minimum points.
From like the sine and cosine graph. It'll make sense when you see it. And you convert your midpoints, not your max and min, but your midline points, those convert to vertical asymptotes. And then you bounce the parabolas off of the max and min points as solid curves. It's really easy. You're not going to have any trouble with it. But I will pause and give you a minute to take the notes. Okay, so let's take a look at just the parent function y equals secant of x. Now you can never start straight graphing just secant. What you do is you convert it to the guide function. So who's going to be our guide for secant?
Cosine.
Cosine, right, the reciprocal. So we keep everything the same, but we just switch the secant for a cosine. Then you do whatever you have to do for cosine. For cosine, what's the period?
A 0 negative a.
2 pi over b, which is just 2 pi. And that's also the period for secant. Okay? Then you make a table, starting and stopping for cosine at 0 and the period. And remember that cosine doesn't start at 0, 0. It starts at 0a. So the a value for this problem is, and then it alternates 0, negative 1, 0, and back to a. Then you graph that, but you graph it dashed or dotted. So we'll come over here. We'll go out to 2 pi. We'll go in by halves. And we only need to go, since a is 1, up to 1 and down to negative 1. We'll put our points on. We have 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi positive 1. So this is one period of our parent function y equals cosine of x. Does that make sense? Now if I wanted to extend that over to a second period, I could back off into the negatives and do that. But for now, let's just graph it from here. Now the only difference in that graph and what we're actually trying to graph up here for our final y equals secant of x is you take all the points that run through the midline and you convert them to vertical asymptotes. So these 2 points right here convert to vertical asymptotes. So we'll have one at x equals pi over 2, and we'll have one at x equals 3 pi over 2. Then you take all of your high points and convert them to upward parabolas. Now I only have half of this one drawn right here, so I'm just going to put half of it there. Sometimes these graphs will break, off with halves on the end, and that's okay. So there's half of an up there, there's half of an up here, so together those make a full upward. And then down here between these two asymptotes I have a low point, so we'll convert that to a downward parabola. That is one period of the secant function. Does that make sense? Okay, let's just say I wanted to go ahead and I wanted to extend it over 2 periods. So I could back off over here, make this negative 2 pi, negative half pi, and negative 3 pi over 2. And I could just continue with what I was graphing before. This would be this point, this point, this point, and back up to here. So we could continue that cosine function and then use it to continue our secant function. So we could insert other vertical asymptotes at x equals negative pi over 2 and at x equals negative 3 pi over 2.
So that's it.
And then I could finish this one, the other side of that one,
And the bottom one.
and this one would make a full, and this one over here would make another half. Right. Does that make sense?
So
That's how you graph secant and cosecant. If you can graph sine and cosine,
That's easy.
you can graph secant and cosecant. But the best thing to do, I've taught it both ways through the years, the best thing to do is if it has a shift, go ahead and shift it while it's a sine or cosine, and then just bounce secant or cosecant off of it. Some people try to shift the final graph and it causes a lot of trouble. It's easier if you shift before you graph it, just like you would with sine and cosine. Any questions about secant? No? Okay. Let's do the same thing but for y equals cosecant of x. So we have y equals cosecant of x. Oh, I wanted to point something out. Can I back up 1 second? Take a time out. What type of symmetry does this graph have? Where could I fold it? Along the y-axis. There is only one other trig function that folds along the y-axis. What is it?
Cosecant.
Okay. It's also graphed up here. Cosine, yeah. Both the secant and the cosine have y-axis symmetry. The other 6 have origin symmetry. So the only 2 with y-axis symmetry you can see right here are cosine of x and secant of x. The other 4 have origin symmetry.
Origin symmetry is like where you fold it down and over.
Right, you would have to fold it into fourths to see it. You would fold it down and then across. Okay. So this time let's actually graph y equals cosecant of x. We'll start with that. We will convert it to its guide function. For cosecant, it's going to be y equals sine of x. So we'll find the period so that we will know where to stop and start our table. The period is 2 pi divided by b, which in this case is 1. So we have a period of 2 pi. We'll build a table for the guide function, starting at 0, ending at 2 pi, and going in by halves. Now remember that because it's sine, it starts through the origin before you shift it. And this one doesn't have a shift, so we won't have to. But if we did, we would still start at the origin before we made our shifts. 0, 0, A, 0, opposite A, back to 0. So there's the table for y equals sine of x. We'll use that to graph one period of sine, but we'll graph it dotted. So let's let this be 2 pi, this be whole pi, half pi, and 3 pi over 2. Okay, so right now it looks like we have this point, this point, and this point. There is your guide graph. Looking at that guide graph, how many vertical asymptotes are we going to see right now? Like, before I extend it. We're going to see 3. How many did we see with secant when we graphed it? We only saw 2, yeah.
There are
So
only
just
2 intercepts.
right. But in this one, we have 3 intercepts. So you use your intercepts there, your midline points. Right here, they become your vertical asymptotes. So let's insert those. And then we will bounce off of the high points to make upward parabolas and the low points to make downward parabolas. So one full up and one full down, you can actually see. That's why I prefer cosecant and sine versus secant and cosine, because they don't cut in half. If we want to extend it over into the negatives, we simply recopy what we have over here. And continue with that pattern. So if I'm coming backwards, I have middle, low, middle, high, middle, low, middle, high, middle. So if I want to do a second period, this is all I have to do. That will give me 2 additional asymptotes here and here. And it will also give me 2 additional parabolas. One upward and one downward. And there is 2 periods of cosecant of x. Any questions about those parent functions? What kind of symmetry does this one have?
Origin.
Origin, yeah. We could fold it along the x-axis and the y-axis. Another way of saying that is opposite points are on there. Positive pi over 2, positive 1, negative pi over 2, negative 1 are on there. So that's how you recognize origin symmetry. Okay, so we're going to kind of cut right there, and then we'll take a quick break and we'll look at just some examples where A and B are not necessarily 1.
Are we going to do any shifts with these?
We are, we will.